Good afternoon, everyone. My name is Kenji Rikitake. This is actually my 7th talk on Neuron Factory in San Francisco. It's been long. My first one was 2010, and I talked many different topics, but today I'm going to talk about something not necessarily of fault-tolerant networks, but about node. Okay, before getting into the details, I'd like to explain some of the basic principles of building fault-tolerant systems. They are, I think many of you have already known this, but I'll explain. Keeping systems stabilized, this is a very important thing. And to make a stable system, the whole system has to be simplified. Don't put too many functions, unnecessary functions. That will almost always cause troubles. And don't be afraid of resetting or restarting a system. This is what we call in the world of Erlang, let it crash. And the system should be able to be dynamically updated on demand for minimizing the downtime, which means that every component, including not only the software but also the hardware, would be much better to be able to be updated. Okay, in this talk, I will explain the barefoot system and sensors, which is a redundant temperature system, sensor system for our own OTP. And I will also talk about the basic design principles, including 8-bit Arduino, which is the platform for the sensor device, and its basics, and the wire protocols, and how Erlang talks with Arduino. I have to skip a slide explaining why the name is barefoot, so I'm going to explain it by my words. Barefoot means BE for beam, AR for Arduino, and fort for fortified. And I scanned it on the Google, and actually there is a place called Barefoot Ridge in New Jersey, USA. I don't know what the place is, but the only thing I know about the place is that it's a very beautiful place in the eastern part of the United States, although I've never been in New Jersey in my life. But anyway, it's called Barefoot. And this is a sensor sealed. I actually made 3, and this is one of them. And they are all identical. I tried to build a fault-tolerant system by myself, but I actually haven't tested the multiple devices. But in this talk, I will explain that all the basic functionality and the components which is necessary for building a fault-tolerant system. So this is basically temperature sensors, a set of temperature sensors, and I made it by my hand, soldered by myself. One digital thermal temperature sensor and 4 analog temperature sensors. Okay, what this can do? This is a digital sensor, and these 4 are analog sensors. And I put the filter on this. Filter means a power stabilizer for this, so that it won't fail easily. And all of these sensors are operating independently, no dependencies with each other. Of course, except for one thing, it shares the same microcontroller AVR on the Arduino. So for those who haven't heard about the Arduino, this is what people call the Arduino normally. The company selling Arduino has already sold lots of different configurations of Arduino. Some of them are 32 bits, but the basic Arduino is about 8-bit CPU. It's a very basic stuff. And okay, this is a CPU, and this is a power supply part, and this is a serial interface part. And excuse me, these connectors are all external, for the convenience of connecting the external circuits. And this could be driven by the USB power or external power from 7 to 12 volts. Okay, I'd like to talk about the general style of the AVR development. The main tool chains for 8-bit AVRs are like the one in old MS-DOS days or much older days when people are typing the assembly language or machine language by hands. It's all about GNU-C compiler, assembler, program loader, and the library. And it's about the event loop. So archaic, but you have to survive with that. What I want to tell you is that you cannot do so many complex things on this Arduino, basic Arduino type of sensor. You have to keep it simple. And during the programming phase, of course, you can use some kind of an in-circuit emulator or in-circuit debuggers, but you usually try and if it fails, you just pull it out, reprogram, and just doing that kind of trial and errors. And on this, on AVRs, interrupts are for timer only. Timer only. This means you cannot do much about interrupts. There are many other ways to use interrupts on AVRs, but basically you should only use it for the timer output or waiting for some kind of period. Or otherwise, you'll be getting into some sort of bugs. Better say Heisenberg bugs, which is very hard to debug. Okay. Before talking about the details on how to deal with the small device, I'd like to show you the usefulness of the chip programmer, which is another external device for doing the doing the many things on the AVR. This is a picture of AVR Dragon, a USB programmer, which is sold by. I bought this in 2008, about $60 or $70, and this is connected to USB as a dedicated device, and it can perform all necessary hardware configuration, from the protection bit configuration or protecting the firmware itself for protecting the intellectual property, and you can use this for replicating chips. Like, okay, this is what we call zero pressure socket. You put the lever up, you pull out the chips, and put in a new chip, and put the lever down, and you just repeat it for replicating lots of chips. You can use it in this way. So I suggest to have this kind of an independent chip programmer if you want to do the development on the AVR or any other kinds of chips. Okay, let me talk about the hardware principles on the making a fault-tolerant system. First, you need to make this a stable hardware. There are a lot of tips, and keep it simple. And the hardware should be capable to be able to reset when something goes wrong, which is, in other words, ready to crash. I'm not saying that let it explode or something, but you should be able to let it crash. Okay, I see a lot of examples for Arduino actually made on breadboards. Breadboards are not something glued or soldered. It's like a pinpoint connected to with independent wires with a lot of holes, and they are so convenient because you can change configuration without a lot of effort. But those contact pins and wires are usually very fragile, so I suggest soldering instead. Soldering means, doing this kind of stuff, soldering. And I'm not going to the details of soldering, but there are lots of tips about soldering. So if you want to know about the tips, ask later after this presentation. Okay. So I talked about soldering, and the second important thing is that keeping the small number of contact points as smaller as possible. This is to prevent contact failures. Every mechanical part will fail. So every connector may fail. And the problem, and the general problems on the USB device is that if you keep the USB device connected, there might be some sort of a contact failure happening if not in a short time period. It should be in a very long time period, or even 1 or 2 years. So you eventually have to pull it out and pull it back on. To summarize, contact failures will eventually happen anyway. So you also need to prepare to design the circuit for the consequences of the what if contact failures occur. So there are briefly 2 kinds of contact failures. Number 1 is open circuit, and number 2 is short circuit. Open circuit means losing contact, and short circuit means 2 independent points which are accidentally connected. So, and both cases may cause hardware malfunction, and you have to be very, very careful not to make the short circuit between the power circuit to blast, especially if you are trying to drive a circuit on a lithium polymer batteries. The internal resistance of the battery is very low, so it will blast and cause fire, and TSA will catch you. Seriously speaking, you cannot check into the lithium polymer batteries. You shouldn't do that. Okay, let's talk about the open contact failure. Usually, I assume usually signal path like this works okay, but on open contact failure, it's disconnected. And the disconnection on this point will cause this point voltage or current or whatever passing, including digital signal, very unstable. And I've found many of Arduino examples leave input open if disconnected, and that is very bad because some kind of static voltage can hit the open input, or other than that, making things unstable. So a very fundamental tip to prevent this point become unstable is that to add a register. In our case, for our temperature sensor, it was grounded because the ground because that is more easier to handle than pulling it up to the power supply voltage. But anyway, connecting at this point with the some sort of a high impedance register will make the here stable. And resistant against any kind of static voltage. So this is a recommended practice. And about this open circuit failure, I'm going to talk about my experience. This is a normal state. This is a normal state when temperature gradually going up and gradually going down. And when the open contact failure occurs here, I first expected this kind of flaring voltage will occur so that some sort of anomaly analysis of the converting this voltage into the digital information could detect this. But the reality was different. It's just the voltage shifted a little bit, but the change was very slow. So it could hardly be distinguished from this stable state. This fact also suggests that I should make the input to the ground, and on LM60, the minimum output voltage is about 0.17 volt or 170 millivolts. So it won't be coming right here. So if once it comes to the ground, this is very easily be detected, and you can immediately detect this is a fault. I mean a sensor fault. So I talked about the open circuit, and next I'm going to talk about short circuit failure. When a digital signal line accidentally makes a short circuit to the ground, signal transfer is no longer possible on the line because it's going to be forcefully set to the lower L level or H level, L or H, it's binary. So in this example, two devices communicating with each other, and accidentally the clock goes down to the fixed to the low level. So the clock between this and this device is disrupted because of the short circuit. And when I intentionally created this situation on this device, it's actually very easy. The only thing you should do is to put the coin between these two terminals. And that caused the whole software halted. And so this kind of failure is very hard to prevent. So, so I think this kind of failure should be treated as a permanent. If intermittent failure, that should be that the sensor will be revived by the Reddit crash principle. But if it doesn't, the sensor will be permanently in fault, so it should be removed. So, okay, I explained open and short circuit failures, and another principle on hardware is that keep it simple. Don't try to do many things. AVR is slow. The clock frequency is 60 megahertz. It's much slower than 1.6 gigahertz or something like that, 1/100th of modern computers, like here, like what is here. Actually, this is a MacBook Air. And so keeping the firmware code small is essential for robustness. And don't try to do many things. I mean, for example, the value conversion or other input-output formatting on the Arduino side, because it takes a lot of CPU power. An fprintf of C function may increase the size of the firmware 2 kilobytes or 3 kilobytes just for an fprintf. So don't do that. Just return the raw sensor values. Also, the tunable hardware parts, such as variable resistors or variable capacitors or whatever variables, including mechanical contacts or moving mechanical contacts, those are inherently unstable and may easily fail. So don't use them, if possible. If possible, don't use them. Okay, and let's talk about Reddit crash principle from the hardware point of view. On Erlang, this is very easy. But on hardware, the only thing you can do to perform this, facilitate this principle is to reset the hardware altogether and to restart it so all the Heisenbergs will be gone by reset. And allowing external reset is required for restarting from Erlang anyway. And so that the Erlang can control this device. And in a more critical case, sometimes you have to use the hardware called, internal hardware called watchdog timer. Watchdog timer is a totally independent timer which is embedded in a CPU chip, although CPU, I mean the AVR chip, and it's totally independent from AVR, and if AVR does not sign the watchdog timer for a certain period, for example 50 milliseconds or 100 milliseconds, the watchdog timer will force AVR to reset. So it's a kind of a let it crash principle implemented in hardware. So how to reset Arduino from USB or any kind of software, including Erlang? The answer is turning off serial signal for 50 milliseconds and turning back on. Maybe 100 milliseconds will be okay, but the 50 milliseconds is a suggested value on the Michael Santos' Erlang library called the SDK 500 and SIY. Yeah, that's it. What this does is that this is kind of list comprehension, but actually writing a loop, because the sequence is off and on, this is the variable status, and the status goes into here, and it's turned off, 350 milliseconds, turned on, 350 milliseconds, and that's it. Okay, so until here I explained about the software, hardware, and now I'd like to talk about the software side of principle on communicating with Arduino. First, you need to have a simple and robust wire protocol, and you often need Erlang to reset Arduino so that you can let it crash. And you also need to override Arduino firmware for hot code swapping. The wire protocol between Erlang host and Arduino should be simple as possible. Because listening to the serial port on the for example, I'm actually connecting this device to the Mac over here, but if this is trying to send something always, the Mac actually have to process it and discard it. For example, if a 9600 BPS flow of 40 bytes on every message continuously sent from this device to a Macintosh, a Mac Mini, which is actually I use at home, it takes 0.4% of CPU. And it's not that small. It's not negligible, although it's small. So when you try to connect a lot of devices, maybe 100 or 1,000, you shouldn't do that. So the host should ask the device first. The polling, that's what I write here, polling. Host polls the device, then the device answers. That kind of protocol will make the things more environment friendly. And using fixed length output for Arduino is also effective, as well as minimizing the number of tuning parameters for keeping the sensor system stable. Okay, why fixed length is important? Let me explain about the serial line protocol. How many of you have used modems? Raise your hands, please. About 1/2. Yeah, time flies. The modems are the very old device to communicate to the internet or whatever, between a computer and computer. And modems in 1980s were using serial line protocol. And the problem I faced during the modem programming was that serial ports had no data framing. It doesn't make a packet for you. If you want to send a 22 byte, for example, 20 byte packets, the easiest way is to put into the Ethernet some sort of API. And nowadays, the Ethernet API will convert it to an Ethernet packet of 20 bytes or whatever with header. which is absolutely easily decodable. But for serial lines, serial ports have no data framing. So you should expect receiving data not from the beginning. And this is very hard to decode if you are not trying to synchronize the transmission. So this is another benefit of polling, because when you decide to poll the device from the host, you can discard all the data before the polling. And you poll the device, then you try to wait for the answer. And if the answer is fixed length, for example, 20 bytes or 16 bytes, and you receive 16 bytes altogether, and you verify the packet whether it's okay or not, and that's it. So for fixed length is much easier to handle. And on Erlang, you can always use pattern matching. Pattern matching is very well suitable for this kind of purpose. And minimizing the tuning parameters, it also makes the sensor system idempotent. Idempotent means not affected by the hidden states. And this is also better practice. So how do you control the serial line from Erlang OTP? A very talented hacker called Michael Santos has released quite a few interesting Erlang libraries for communication. For example, he has released a package called Procket for Ethernet, and he also released a package called SRLY. I don't know how should I read? Maybe sorry or something like that, but I don't want to use the word, so I'll call it SRLY in my presentation. But SRLY has a lot of advantage. It uses the native interface functions, or NIFs, and calling directly to the operating system interface of setting what people call so-called line disciplines. I don't know why lines have to be disciplined, but it's the details of how do you set the serial line, such as speed or setting the line up and down or something like that. So anyway, this SRLY library is very useful. And this library also has a fixed length reading function with timeout, which is very useful on communication with Arduino. So here's wire protocol. It's just listing the number, device ID, and all sensor output. They are all 16 bits. And I wrapped it with the, this is the ASCII code SDX and ETX. I don't know whether anyone knows about this, but this is actually a start of transmission, and this is end of transmission. So defined in ASCII code. And in other words, this is just number 2, and this is just number 3. But anyway, I respect ASCII code original meaning, so I use them. And coincidentally, ETX is actually Control-C. But anyway, there's a magic number, and I set it to some number, which I'm going to explain in the next slide. Okay, this is a piece of Erlang code. It's actually binary matching from here to here with a lot of attributes, but this is basically about specifying little endian integer, lower byte first. And this is convenient for AVR, so I chose little endian format. And one of those are set signed, while the rest of those are set unsigned. Because the second ADT, I mean the digital sensor output, is more convenient to be treated as a signed number output. So I only do this, and this effectively decodes the data from a 16-byte packet into six parable integer. If the magic numbers are all matched, and I set the magic number here, 8255 in hexadecimal. And for those of Do you know what 8251 means? Maybe not. Okay, this is the name of the Intel chip in 1970s, 8251, for 8080A CPU. It's about the UART serial interface. Just trivia. So forget it, please. Okay, the phrase "related crash" is popular among the Erlang community. Fred Abel over there, who kindly came to this presentation, again, thank you, Fred, the author of Learning Some Erlang for Great Good, recently explained the phrase in his blog article, the Zenab article, as a principle of transforming failures, exceptions, and crashes into tools we can use. I'm pretty much impressed by this explanation, actually. And so you can use whatever. Sometimes you use failing system as a tool, but this related crash is much more moderate way of using a reset or other hard restart features to control failures. And on Arduino, unfortunately, you don't have much choice. You need to reset the AVR chip under Erlang's control. Okay, and there's another thing on Arduino. Erlang allows hot code loading, and you can update the code of a function without stopping the entire Erlang node. But on Arduino, you can update Arduino remotely, but it's not that easy. You have to rewrite the firmware code under Erlang's control and the bootloader's help. It takes 5 to 10 seconds, practically. But it's feasible. And feasible is much better than not feasible. And it's very useful on actually debugging the firmware, or sometimes you have to remotely debug the Arduino or any kind of AVR chip, which might be connected to Raspberry Pi or other more intelligent device nodes, which might be running Erlang. So let me show you the example of the memory model. AVR has two distinct memories. You cannot run the code from random access memory. So no one can do the bad thing here. It's a very strict protection over here. And so the AVR programmers use RAM only for stack, work area, and other volatile stuff. And you cannot use not much RAM. It only has 2 kilobytes. And on the AVR, the code resides in the flash memory. It has 32 kilobytes, but you have to have a bootloader if you want to control it from some sort of remote communication. And AVR has a hardware protection mechanism for the bootloader section. On a regular Arduino, it's only 256 bytes. But in my case, I had to enhance the bootloader code a little bit more. So I chose 512 bytes here. And that section is completely protected from the external access unless you reprogram it by a chip programmer such as AVR Dragon. So normally you don't have to worry about this part being rewritten. And so when you try to access to Arduino from a remote Erlang or whatever software, you use bootloader. You call bootloader to rewrite this user code according to the external input. And I forgot to explain this one. Other than the flash code, Arduino or AVR has a section called EEPROM. EEPROM is a non-volatile permanent storage which will survive the reset or even a power off or power cycle sequence. So in this part, you usually put some sort of a device-dependent data, such as a device ID, which is a permanent ID, like those in SIM card of your cell phones, or some kind of a persistent data which is retrieved in a long-term measurement and should not be forgotten on the, in case of accidental reset or power cycle. Okay, so this is a piece of Erlang code for the dynamic update. It reads the firmware file as an earn term right here, and this is a file name. And break it into chunks of 120 bytes. Actually, this is a list of binaries. And opens the communication channel. This is a very lengthy device name, but this is the actual name on the Mac Mini. And this part may differ if you use FreeBSD or Linux or, well, it might be Windows sometimes. And all you've got to do is to invoke this function, load it. And the loader speaks all the protocol and commands, send the command to the Arduino to quit. And after sending quit, the bootloader will immediately handle the control to the user code. So that's how the reset sequence goes on. And the protocol details are described in an AVR application note, and so you can find it online. And if you don't know about, if you can't find it, ask me later, and I can give you the information about all the details. So before explaining the whole slides, I think I can do some demo. So let me do that. Okay. Actually, during this speech, this poor little sensor has been measuring temperature every 1 second. This Chrome polls the device. So this stuff is changing. I know this is not a good way to do the demo, but I just can't. I'm not a very good web front-end programmer, so this is all I've got. And an interesting part is that when you put the plug of this digital sensor, it shows fault. And sorry for my eyes, I'm a very old man. And when you put it back, like this, it revives. And when you do the same thing to the analog sensor over here, for example, fault. Okay? And you put it back, yeah, my eyes, it's hard. When you put it back, yeah, it's back and showing slightly higher than the ambient temperature because of my body temperature. Body heat is transmitted to each device. So this is a very simple demo about how to detect a fault immediately, or better say, about using the polling, so that all the state in this device can be communicated to the here. And some people may complain this can be done in Ruby or this can be done in Python, but I should tell you that this is actually done in Erlang. This is a part of Yaws code. Yaws is the name of the Erlang server. It's not cowboy, and it's a little bit old-fashioned, but it's stable, and it runs as an independent server, like an Apache web server, and that is very convenient for me. And it has a very interesting feature. When you declare Erl, the whole HTML, supposed to be HTML, turns out to be Erlang code from here. So I write the old functions that gives us some sort of style changing of the CSS. And you can even call external functions from the Yaws, which is inherently very insecure, but this is not about security, and this is about convenience. And when you do it safely, it's okay. You just can put it in a Docker container or FreeBSD jail or whatever. And this is the core part. Out this out function does the whole computation when the page is being loaded. Out is being called, and it opens the device. Do test is a sort of convenient function I made for it. It's not just testing. It actually does the polling. Polling and get the data and close the device just in case. And it generates the whole, this complicate style of the actually tuple and list, and I don't know. Yeah, this is actually a single tuple with lots of nested lists and tuples, but this is effectively representing the structure of HTML, and this is a feature of eHTML, which is a feature of Rails, and this is very convenient when you think about designing a web page on Rails, and within this data structure, you can build in a function, and this is very convenient for converting stuff, or you can put into some sort of conditions so that the value changes when the input change. And I'm a lazy programmer, so I didn't use risk comprehension here. I just listed all the stuff, and it ends. The URL tag ends, and the body ends, HTML ends. So that's it for the HTML. And yeah, that's it. All right, and this is the smaller function. When you want to do output in just a more character user interface, you can use IO formats like this. Okay, so this is the end of the demo, and back into slides. Yep. So I'd like to explain the issues and further directions to conclude this presentation. I've explained how a sensor capable of fault-tolerant operation can be built, but there are still unresolved issues. For example, when you pull the plug of this USB, I'm not going to do that now, but sometimes, especially in a buggy operating system, pulling the USB causes system crash. Why? Because fundamentally, the communication between the USB device are all wrapped into a software. And when you try to detect a fault on the software, you have to use some sort of a heuristic like timeout. And in case of Mac Mini, well, it takes about 10 seconds to detect whether the device is unplugged. And that is actually very slow. So when you deal with the USB failure, you have to be very prepared, or otherwise you get into a lot of trouble. And there are other issues. Calibrating the heat sensor is actually very difficult. You should, all you can do is to put this in a very stable ambient environment, or you put into some liquid, actually ice water or something like that. Of course, you have to cover this on a vinyl bag, or otherwise you're getting in a huge trouble. But it takes time, because heat capacity of these devices are not negligible. It takes at least 10 minutes or something like that, and sometimes an hour to make the whole sensor stabilize. So it's very hard to do it in software people's rhythm or speed. And in this presentation, I didn't mention details about modeling the fault-tolerant operation, but that depends. All I can say about this operation data, it depends. You can average the sensor values. For example, if you have 4 sensors. But what if it's going to be 3 or 2 or 1 or 0? You have to change the mode and how to remove the failed values is not that trivial. And if you, there's an IBM research paper about how Space Shuttle try to deal with the fault, lots of accidents with five independent computers. But the failure mode, dealing with failure mode is not that trivial. You have to notify, the computers has to notify the astronauts before shutting down the system. Otherwise, the mission will be aborted, and there will be precious casualties of astronauts. I'm not joking. And this shows the difficulty of how modeling fault-tolerant operation is difficult. You have to evaluate the pros and cons. Okay, for future directions, I've tested this sensor outdoor when it wasn't raining, and it worked. But more rigorous field testing is certainly needed for verifying the reliability. And I like to use this together with a Raspberry Pi, because Raspberry Pi runs Erlang, so actually makes a very good fault-tolerant sensor. And of course, I need to pursue using multiple sensors and nodes simultaneously, though it's definitely not an easy task. Okay, and I extruded a lot of things from this talk. On the real-world IoT, you have to deal with MQTT or co-op or some other difficult protocols. I have a doubt whether this kind of protocols can be spoken from a remote device without thinking about the power dissipation or power consumption. But anyway, and I didn't talk about cryptographic security because it takes a lot of CPU time, not on the Macintosh, but on the AVR. And the host device driver, this will be an important issue because it's very hard to debug. And some people, especially those dealing with the latest Arduino, don't have to deal with the 8-bit CPU. They can program with a 32-bit CPU, so maybe those may be running Linux or whatever the more sophisticated operating systems. And there was a talk about implementation called Erlang AO. And Erlang AO, I actually had training on Erlang AO in Erlang Factory 2013, sorry about that, 2013. And it was for Raspberry Pi, so I intended to exclude it from this talk, but Erlang AO is actually a very good example, so you should take a look. Okay, and a lot of related works will be found on my slides, so I'm not going to explain the details now because the time is constrained, but there are lots of tools, and you should take a look at them. And there are at least 2 related talks on Factory San Francisco Bay. On 2013, Omar Kirek talked about Erlang AO. And on 2015, there was an excellent talk about how to control a robot on Elixir. And Frank Hanless did a very good job about that. You should see their presentations. Okay, so thanks. I'd like to say thanks to Michael Santos, because he did lots of interesting things. Although I don't know whether he gained popularity on that, so I should mention him here. And I should say Erlang Solutions for allowing me to do this talk. And I have to thank you all. Thank you for listening to my talk. So thanks again. Any questions? Any questions? Yes?
So if you weren't going to use USB, what would your other options be for something maybe a little more reliable?
Okay, the question was, if not a USB, what would be a more better alternative, right? For example, Erlang LE can control the GPIO or general purpose IO directly from the Erlang, their functions. And using the GPIO or I2C, which is a protocol between the sensor device and the CPU, or SPI, that is another protocol, directly from the CPU will remove the problem of the USB connection and disconnection, or built into the USB control tree, or removing it. So, I do not suggest using RS-232C or other older protocol, because it would have the same problem, although there won't be a connection or disconnection problem. The whole problem is based on the details are materialized by the software. Is it okay for you? Okay. So, any other questions? Yes?
I know this is exactly the opposite from Keep It Simple, but if you look at Bluetooth,
yes.
How does that fit with your model?
Okay, the question was what if Bluetooth being used on this kind of application, how it fits on the model. I intentionally excluded Wi-Fi or Bluetooth for the exact reason, because the same reason of the USB, because it's heavily based on software. And I've been a ham radio operator for 40 years. Actually, today is the 40-year anniversary of my ham radio license in Japan. And radio is very unstable and unreliable. For example, when you think about bit error rate of the the difference of wired connection and radio connection, the radio connection will have the error rate of 0.1%, and the wired connection will have much less. About the difference will be the difference of the bit error rate will be 10,000 or even 100,000. So I do not let me opinionate a little bit. I do not believe in wireless application unless you have to use it. For example, Wi-Fi, and Bluetooth will be okay, and Bluetooth LE will be okay, but you have to write a lot of code and you have to do a lot of testing for that. So I intentionally excluded from my choice, but I understand your question, and your question is 100% valid. Any other questions? Okay, so I conclude it. Thank you.